In this video we will primarily focus on the blackbody radiation. In the whole video we will focus on what is blackbody, then it is the practical results regarding the blackbody radiation, and some classical theory regarding blackbody radiation. And we will see that the classical theory regarding blackbody radiation was not matching with the practical results. So later on Max Planck came, he published his paper on 14 December of 1900. Then in his paper he derived some theoretical result regarding blackbody radiation which perfectly match with the practical results, which is known as quantum physics nowadays. Max Planck's theory and all the other theories in the early 19th century is known as the old quantum physics, and we will primarily focus in the lecture series on the old quantum physics. First of all, we will see some basic definition which we will encounter throughout the video. First of all is the thermal radiation. Thermal radiation is nothing, it is the radiation emitted by any body due to its temperature. Like due to temperature, the constituent particles started moving, it's like started colliding with each other, which give rise to a radiation that is known as thermal radiation. We will see that almost all the in condensed matter that is solid or liquid, the radiation emitted by condensed matter are almost independent of the matter. Okay, means we will see the similarities between the radiation emitted by any kind of condensed matter. But if we go to the details, we will see that there is some difference between the radiation emitted by to different condensed matter, but there is some kind of bodies for that emits the radiation of universal character, that is known as blackbody. By definition, blackbody is something that it absorbs any kind of radiation incident on it, and it emits all kind of radiation, like it emits a continuous spectrum of radiation. So blackbody is a kind of body that emits the radiation of universal character, which makes it the chief interest of physicists. And we will later see some kind of practical blackbody. Before that, we will see a kind of device that is called optical pyrometer. So in the practical life, if we see that if we burn something, it will turn red, then it will go to white. So as it gets hotter and hotter, it changes its colors. Okay, so there is a relation between the temperature of the body and the wavelength or the frequency of the radiation, which is utilized in this optical pyrometer, which is used to estimate the temperature of a stellar mass by looking at the frequency or lambda of the radiation emitted by it. Okay, then we will go to another term, that is spectral radiancy. Spectral radiancy is the energy emitted by a black body by per unit time and per unit area in the frequency range from nu to nu plus del nu. That is called spectral radiancy. Then spectral radiancy is the characteristics of a black body at particular temperature, absolute temperature T. we will see how it is important later on. Then there is another term that is called radiancy. Radiancy and spectral radiancy is related as so if we integrate, sorry, there will be a del nu, because we will see the significance of this relation. If you look at it, we have integrated spectral radiancy from 0 to infinity. So it is what was spectral radiancy? It was the energy emitted by blackbody per unit time per unit area at particular temperature T and particular at this frequency range. So if you integrate this term from for all the frequency, means we add up all the spectral radiancy for all the frequencies starting from 0 to infinity, we will get RT, that is the total energy emitted per unit time per unit area by a black body at the particular temperature T. That's it. Then there is another law, that those are empirical law, and like those came from observation primarily. So that is one. First of all is Stephen's law, that is radiancy is related to the absolute temperature as T equals, this is Stephen Boltzmann constant, which is equal to 5.67 to 10 to the power minus 8 watt, that is means energy per unit time, that is in SI unit watt, joule per second, then per meter cube, and Kelvin to the power minus 4, because there is a temperature dependence. Like the another law is that Wien's displacement law, that is nu max. We will see what is nu max very soon. Now for describing all two laws, we will have to look at the graph, experimental graph of the spectral radiancy and nu, that is the frequency. If you look at the graph, you will see that at very low frequency, the spectral radiancy, that is energy emitted per unit time per unit area, is very low, and as it keeps on increasing, it reaches a very high peak, and it again keeps on decreasing after that peak. So we will see that this graph is different for different temperatures. Like here I've drawn 3 curves corresponding to 3 temperatures, not to scale, and these 3 temperatures are related as, so T3 is higher than other two. We will see how it is. We can imagine this, we can relate these to 3 curves to practical life. You can see that for a particular frequency, the curve is increasing for different temperatures. Okay, and for like we will, if we take the peak value, the frequency corresponding to peak value 1 is nu 1, frequency corresponding to peak value 2 is nu 2, and the third one is nu 3. So we will see that as the temperature keep on increasing, frequency also keep on increasing, and on the other hand the lambda will keep on decreasing. So in practical life we often see that as the temperature of a body keep on increasing, the radiation emitted by it, the color emitted by it also keeps on decreasing. Like for a very much hotter objects emits red color, then it goes white and all. So it's nothing, just and this relation is depicted in this difference balls winds displacement law. So the frequency, maximum frequency, that is frequency corresponding to the peak value, is shifted according to directly to the temperature of the black body. We can write this law as another way also, that is lambda max into absolute temperature is equal to a constant. This constant is Wind's constant and is equal to 2.898 into 10 to the power minus 3 meter Kelvin. Okay, that's it. And how can we relate the Stefan's law to the curve? We will see that for a like in okay, for like first we will see how this in the y-axis there is spectral radiancy, and what is radiancy here. Radiancy is nothing, just the area under the curve, that is the total energy emitted by a black body at the particular temperature. So we have seen that as the temperature is keep on increasing, the area under the curve is also keep on increasing. That means the total energy emitted by the black body is keep on increasing. So that is the radiancy is keep on increasing. And experimentally it has been found that radiancy is related to the absolute temperature as this law.